Aryl halides. Their introduction. Aryl halides are aromatic halogen compounds in which the halogen is directly attached to an aromatic ring. They are assigned the general formula ARX, where AR is a phenyl, is a substituted phenyl or some other aryl group, such as naphthyl. For example, we have chlorobenzene, O-bromotoluene, M-bromotoluene. Nomenclature. Aryl halides are named by adding appropriate prefix of the halogen chlorobromorido and its position if necessary to the name of the parent aromatic compound as illustrated below. Bromobenzene p-iodotoluene 1,2,3,5-tribromobenzene. Their methods of preparation. Aryl halides are generally prepared by the following methods. First is nuclear halogenation. Aryl halides and bromides can be conventionally prepared by the direct chlorination or bromination of aromatic ring. This reaction is generally carried out at low temperature in the absence of sunlight and the presence of Lewis acid such as ferric halides and aluminum halides, which acts as catalyst. The catalyst is generally known as halogen carrier. The usual practice is add to the reaction mixture some iron filings which are converted to the halogen into the corresponding ferric halide which acts as the Lewis base. For example, chlorobenzene is obtained when benzene is reacted with chlorine in equivalent quantities in the presence of ferric chloride obtained in the situ by reaction between iron and chloride. Halogenation normally stops at the monosubstitution stage, but if halogen is used in excess, a second halogen gets introduced, mainly into O and P positions with respect to the first. Similarly, toluene may be chlorinated or brominated in the presence of iron at low temperature, the reaction taking place more readily than in case of benzene. Next is from diazonium salt. The decomposition of diazonium salt under suitable conditions is probably the best method of preparing aryl halides. Aryl chlorides and bromides are obtained by treating the diazonium salt with solution with cuprous chloride dissolved in HCl or cuprous bromide dissolved in HBr. This reaction is known as Sandmeyer's reaction. It may be seen that in the Sandmeyer reaction, it is the halogen from cuprous halide which gets attached to the benzene ring. In place of CuCl or CuBr, it is also possible to use copper powder and HCl or HBr. The reaction is then known as Gattermann reaction. Iodo compounds are obtained just by warming the diazonium salt solution with aqueous potassium iodide solution. The diazonium salts used in the above reactions are themselves obtained from aromatic amines treatment with diazonium with sodium nitrite and an acid such as HCl at low temperature. That is, fluoroarenes are prepared by decomposition the corresponding diazonium tetrafluoroborate by the action of heat. The fluoroborate itself is obtained by the diazotization of a suitable primary amine. This reaction is known as Balzheimer reaction. Next is from organothallium compounds, a recently discovered method for the introduction of halogens into a benzene in a very specific way involves the use of thallium trifluoroacetate. Arenes undergo electrophilic aromatic substitution with thallium trifluoroacetate in fluoroacetate acid to form thallium bis trifluoroacetate, which reacts with potassium iodide to form aryl iodides. Now the physical properties of aryl halides. First is physical state. In general, haloarenes are colorless, oily, liquid or crystalline solid. Second is density and solubility. They are heavier than water and insoluble in it, but they are soluble in organic solvent. The para compound being generally less soluble in a given solvent than the ortho isomer. This fact is made use of separation of ortho and para isomer. Third is melting and boiling point. The melting and boiling point of haloarenes are nearly the same as those of N-alkyl halides containing the same number of carbon atoms. Amongst themselves, the melting and boiling point increases as the size of the halogen atom increases. In other words, for the same aryl group, the melting points and boiling points follow the order iodo greater than bromo, greater than chloro, and greater than fluoro. For the same halogen, the melting and boiling point increases as the size of the aryl group increases. Next is for ortho, meta and para isomeric dihalides. The melting points differ very widely while the boiling points show much less variation. For instance, the melting points of ortho, meta and para dichlorobenzenes are 256, 249 and 325 Kelvin respectively, while their respective boiling points are 5, 453, 446 and 448 Kelvin. Next is the para-isomer has relatively very high melting point. This is because the para-isomer is very symmetrical and fits better in the crystal lattice. Therefore, it requires much more energy to break the crystal lattice. Their chemical properties. The chemical behavior of aryl halides is marked by lack of reactivity under ordinary conditions. Unlike alkyl halides, aryl halides undergo nucleophilic substitution only with extreme difficulty except in the presence of suitable substituent. Moreover, the presence of halogen also deactivates the aromatic ring towards electrophilic substitution. The few important reactions which aryl halides do undergo are described below. First is nucleophilic aromatic substitution. It has been stated above the simple aryl halides don't undergo nucleophilic substitution under ordinary conditions. However, they can go so under strong conditions involving the use of a high temperature, pressure or very strong nucleophile reagent as illustrated below. First is replacement by hydroxyl group. Aryl halides undergo nucleophilic substitution by hydroxy when heated with aqueous sodium hydroxide at about 6 to 3 Kelvin and high pressure. Next is replacement by amino group when an aryl halide is heated with aqueous ammonia in the presence of Cu2O and at high temperature the halogen atom is replaced by amino group. Next is replacement by cyano group. Alkyl halides react with cuprous cyanide at about 473 Kelvin in the presence of pyridine to undergo replacement of halogen by CN group. In addition to the reactions discussed so far, aryl halides also undergo the following reactions. First is formation of Grignard reagent. Aryl bromides and iodides readily form Grignard reagents in the presence of dry ethyl ether as a solvent. Aryl chlorides don't readily undergo this reaction in the presence of dry ether. However, they do form Grignard reagents if dry tetrahydrofuran is used as a solvent. Second is Wurtz fitting reaction when an aryl halide is treated with an alkyl halide and sodium metal in the presence of dry ether. The halogen atom of aryl halide is replaced by aryl group. Next is fitting reaction. If only aryl halide is heated with sodium in the presence of dry ether, diaryls are formed. Next is Ullmann biaryl synthesis. When heated with cuprous powder in a sealed tube, aryl iodides form polynuclear compounds. Next is reduction. Aryl halides can be reduced with NiAl alloy in the presence of alkali to form corresponding hydrocarbons. Fifth is oxidation. On oxidation of nuclear halogen atoms which contain a side chain also, halogen atom remains intact while the chain is oxidized to carboxyl group. Relative reactivity of aryl halides with respect to alkyl halides. Reason for low reactivity of aryl halides. We have seen above that simple aryl halides exhibits very low reactivity toward nucleophilic substitution reaction. This behavior is in sharp contrast of that of alkyl halides which are highly reactive compounds. Let us now try to see to why the halogen in aryl halides is rather inert towards nucleophilic substitution. Explanation based upon resonance. An aryl halide is a resonance hybrid of various contributing structures such as structures 1 to 5th shown below in case of chlorobenzene. It is evident that therefore that the molecule of an aryl halide is resonance stabilized. Moreover, the contribution of structure like 3rd, 5th imparts a partial double bond character to the carbon halogen bond in the resonance hybrid of the aryl halide. In other words, carbon halogen bond is in aryl halide is stronger than a pure single bond. Thus, in contrast with alkyl halides, aryl halide exists in the form of resonance stabilized molecule in which the halogen is firmly attached to the carbon. As such, the halogen in aryl halide can be easily displaced by nucleophilic reagents. The above interpretations of the low reactivity of aryl halide is also supported by their dipole moment values. For instance, chlorobenzene has dipole moment of only 1.75 diopter, while the dipole moment of alkyl chloride are of the order 2 to 2.2 diopter. This means that aryl halides are much less polar than alkyl halides. This is obviously due to the fact that contributing structures such as 3rd to 5th of aryl halides contain halogen carrying a positive charge. Contributing from such structures tends to oppose the development of negative charge on the halogen arising from the displacement of electrons of carbon halogen bond towards the electronegative halogen atoms, even though there is still a net displacement of electron toward halogen in aryl halide is less in alkyl halide. This naturally inhibits the displacement of the halogen. Comparison of reactivity of nuclear and side chain halogen compounds. Reaction of side chain halogen compounds. In order to compare the reactivity of nuclear and side chain halogen derivatives, let us first have a look at the reactions of side chain halogen compounds. Side chain halogen derivatives resemble alkyl halides in their chemical behavior and are very reactive in nature. They undergo a number of nucleophilic substitution reactions as well as other as summarized below. Reaction involving halogen atom. First is reaction with alkalis. When benzyl chloride is react with aqueous potassium hydroxide forms benzyl alcohol. When benzyl chloride react with aqueous KOH, it is form the compound which is unstable and then it loses the water and form benzyl dihide. Next is reaction with ammonia. When benzyl chloride react with alcoholic NH3, then it form benzylamine. Next is reaction with potassium cyanide. When benzyl chloride react with KCN, it forms benzyl cyanide. Next is Wolff-Fitting reaction. On treatment of side chain derivatives with alkyl halides or other aromatic halogen compounds in the presence of sodium and triether, the halogen compound is replaced by alkyl or aryl group. Next is Friedel-Crafts reaction. Side chain derivatives react with aromatic hydrocarbon in the presence of anhydrous aluminum chloride to give higher hydrocarbons. Next is reduction. Nascent hydrogen from zinc copper couple and alcohol reduces these compounds to yield hydrocarbons. Next is reaction with magnesium. Like nuclear halogen compounds, side chain derivatives form Grignard reagent on treatment with dry magnesium powder in dry ether. Next is oxidation. Action of oxidizing agent result in the oxidation of the side chain including the halogen atom present in this chain. Mild oxidizing agent like lead nitrate convert the side chain into CHO group while reagents like nitric acid change into COH group. Next is halogenation of side chain. On treatment with halogen at high temperature in the presence of sunlight and absence of halogen carrier, the side chain gets further halogenated. Thank you.